Yeah, hi everyone. So my topic today is the Wi-Fi radar. It is a no-cost Doppler radar built around commercial off-the-shelf Wi-Fi components. Oh. So here's my contents for today. Firstly, I will give an introduction about the Wi-Fi radar. Then I will demonstrate how we implement it and design it. And then we will show the performance and some video demo videos. And then finally, I will to outline some future works what we in our lab are currently working on. So first, what is the Wi-Fi sensing? So Wi-Fi sensing uses existing Wi-Fi signals to detect events or changes such as the people motions, like your gesture recognition, and it also can be used some biometric measurements, for example, those vital sign detection, including the breathing or the heart rate, and also in terms of the currently very popular joint communications and radar radio sensing, or the JCAS. So this is also a really big topic for the Wi-Fi sensing. And again, in terms of the cost and availability, Wi-Fi sensing is really good at it, because literally for those Wi-Fi cards, they are very low cost, and they are basically the off-the-shelf components. There are two types of the Wi-Fi sensing. Firstly, it's this one we call the passive Wi-Fi radar, or the PWR. So this is the radar which I have done several times. For basically, it's based on the passive radar technology, and it's used the Wi-Fi signal. Because this is a passive solution, so the PWR doesn't have a direct control with the Wi-Fi signal. It's only listen to the Wi-Fi signal. So it's not it can be a solution, but probably not the best solution. As another one is called this channel state information. So this is a more communication way of the sensing. So the CSI is generated by one of the pilot signal from the Wi-Fi signal. Then using this data, we can do for all those Wi-Fi sensing as well. Also, there will be some others work for the Wi-Fi sensing, including those MIMO Wi-Fi radars, things like this, but those are not currently not focused. So in here, I will present mainly focus on this CSI-based Wi-Fi sensing. So another question here is, what is the CSI? So it's using the existing standard 802.11 based protocols, and it's using these pilot symbols in the OFDM signal. So basically, because at the receiver side, it also loads this pilot signal. So by using this pilot signal, we can calculate this complex volume for the channel as the channel frequency response. So assume we have this transmitter as the Y in frequency domain, and the receiver as X. Then we can write our equation, this Y equals to H times X plus the noise. So the H will be the channel. So in order to calculate the channel, we can simply use the Y to divide by the X. So this is basically just a basic idea how we calculate the CSI with those Wi-Fi cards. And for the CSI data, it has 4 dimensions. Firstly, it will have the spatial domain. So for spatial domain means the number of the receiver and the number of the transmitter. So and then we have a frequency domain. This is meaning based on the subcarriers. So subcarriers it's related to the OFDM signals. And then we will also have the time domain data. So this is related to how many Wi-Fi packets is received in one time. So in overall, you will have from those Wi-Fi cards, you will receive a 4D matrix like this. So obviously, you can see this 4D matrix is going to be quite a large one. For example, if currently very popular, you can use the 3x3 receiver by 3 transmitter. Then if you think about, you have the number of subcarriers is 56, and the number of package will be normally like 1K per second. So in that case, you got quite a big of the CSI data set. Okay, so we have a measurement to implement these Wi-Fi cards to make it work as the way for the Doppler radar. But there are several challenges we need to solve before we actually can use this CSI data. So firstly is the carrier frequency offset. This is because of the crystals for the PLL frequency. They are not identical between the transmitter and the receiver. So because they are not the same, so they will be bring a CFO in the received CSI. So our solution is to on the hardware synchronization. So this is idea is we remove this crystal on the Wi-Fi card and wire it with a cable. So the cable over here, and this one will connect to an external signal clock source. So to do like this, we have customized a PCB board. So on this board, we have a 2 part of the share. And in the left part here, this provides this current for the Raspberry Pi and the Wi-Fi cards. And in the right side, we have this active crystal here. So this one provides for the 40 megahertz of the clock frequency. The result for before and after the with the clock source is very obviously. So in the left here, these are the unwrapped phase difference from all the subcarriers. And you can see these subcarriers, the phase of them, they separate from all the way from pi to minus pi. So basically the phase of them, they basically separate everywhere. And obviously this CSI data is not good to do, those phase information is not reliable. And in the right side, we can see if we use the synchronized clock source, the phase is much close from each of the subcarrier. For this one over here, it's basically just a 2 pi flip for the from here. So basically they quite close together. Then now the CSI data is the phase information is now more reliable now. And here is another plot to demonstrate how this CFO have the effect on each subcarriers in terms of the phase. So this is a polar plot, and you can see without this is without those synchronized clock source. You can see this phase just split all the angles, and when we apply use the same clock source, they are more closed in one area, although they still have quite a bit of the this change, but it's basically shows much better than over here, because this is they also have some other phase errors in the rather than just the CFO. So there are other sources for the phase errors. So then secondly, for another one is the package detection delay. So this is due to the design of the communication system, where the receiver may detect the package several samples period later or sooner than the the package itself, because in this way they think about, you have like a 20 megahertz of the Wi-Fi signal, you could have like 1 or 2 or more samples before or after. So this is also very crucial for the CSI data, and our solution is because in terms of the baseband frequency, they are symmetric. That's because the I and the Q they have passed through the same bandpass filter. Then we can solve this with a very simple way. We multiply the symmetric subcarriers for all the CSI data. For example, if we have 56 subcarriers in this in our system, we got 56 subcarriers. Then what we do is we multiply the first one with the last one. So the first one, the 56, And then we have the second one and the 51. So by doing this symmetric multiplication, we can remove this package detection delay. And here, just to demonstrate how this package detection delay looks like. And if we have this blue line is the original subcarrier, the phase from one subcarriers. If we fit it with different of the order of the polynomial, for example, this is 0 degree, and here is the first order and the second order, third order, and over the right side, we estimate the group delay based on the first order. So basically, this this line we think is the best one to represent for the subcarriers. Then we can see there are clearly two groups of the delay. So so this one, the major group over here, these are thought to be the correct delay, and here this will show to be these delays are due to some package detection delay errors. And here is the overview of our CSI-based Doppler radar system. So firstly, we have two Raspberry Pi. So this is the board on the below. At the bottom, these are two Raspberry Pi, and then there are two CSI cards over here. So this CSI card will connect, each one has three connectors, and they will connect to the outside one will be the transmitter and one will be the receiver. And in the middle over here, this is the customized PCB board as I show. So in the top here, these three connectors is to provide 40 megahertz of the clock source, and the bottom 6 is to provide the power to run those two Raspberry Pis. And of course, we have make this with 6 connections. So in the future, we're also able to expand this system with another 4 Raspberry Pis and the CSI card as well. Okay, so now I just give some performance and demo for this CSI-based Doppler radar. So first, we just put two transmitter, the one transmitter and the one receiver apart at about 2 meters. Then we have a person at this target, and we're walking around this area. So basically walking forward and walking back, just to demonstrate how this transmitter and the receiver with the CSI, with all the proposed concepts, working for the to generate the Doppler spectrogram. So here is the spectrum looks like. So in the left one here, this is the spectrum we can generate for the walking person. And you can see here, this area is the going forward. And this area here is going backward. So basically, this is away from the antenna, and this is close to the antenna. So then you can see they are very clear of the this sinusoidal wave to show how the this person walking close forward and backward from the antenna. And this is the best the spectrogram we have after we have this PDD removal with the algorithm. And in the right side, this is the spectrogram. If we didn't apply our PDD removal, you can see then in this case, in the middle, we can see there's another symmetric of the Doppler curve, just this is incorrect, but it's just in another direction. So basically, this is because there are a group of those package detection delays, and those, if we didn't remove them, they will just occur another part of the Doppler frequency, Doppler shifts. And here I will demonstrate a fan speed detection with our system. And just plug here. Yeah, so so this one basically shows how the CSI system can react to this to use for this the speed of the fan to detection. You can see we can see very clear of those two Doppler trace, both positive and negative domain, and also we can see very clear when there is a change of the speed, and also the in the end when the speed is slowing down over here. And another one is it's based on for the angle finding. So this one basically we apply for another called a near field match filter. Then we have this 3 antenna here as the to put them like an antenna array, and over here this is the transmitter. So basically we want to see the angle from this antenna when we move the antenna from different directions. So you can see the beam due to the angle is changed over the time when I move this transmitter antenna. You can see there's slightly half-second delay. This due to the processing in the system. So, but it's actually quite accurate to show how this the antennas move around in front of those receiver antennas. So our future work currently, firstly, will be the MIMO setup. So as we have the PCB board with additional 4 connections, so we theoretically we can have another. We can make it 3 by 3 CSI card by 3 CSI card. That's 9x9 system in the for a huge MIMO setup, and for those can be used to do those imaging Wi-Fi imaging things as well. Another thing we are currently working on is this frequency hopping, because frequency the Wi-Fi at 5 GHz band, they can span from 5 GHz to 6 GHz. All we need is basically to step the frequency by each of the Wi-Fi channels, so that we can achieve to a UWB radar. In this case, if we can have a UWB radar, we can also do those range detection with a good resolution. Another thing is this two-way CSI transmission, because currently we to remove the CFO, we have used this cable, a physical cable to connect to a transmitter receiver. But in the future, we think if we can use this two-way CSI transmission, then we can avoid the cables, and we can basically from the receiver side transmit the received CSI to the transmitter. Then the transmitter will have 2 CSI, and then compute together. Hopefully we can remove that CFO wirelessly. So that's another very interesting work to do. And also some more applications we can do, just like I show for this source finding, angle finding, and also we can do some additional applications like those device-free localizations, things like this. So there's definitely quite a lot of work can be done with our current system as well. Yeah, thanks. That's my end of my presentation. Any questions?